310 was linear approximations, which we'll actually sort of talk a little bit about to do section 4.4. Yeah. Okay. But, so I was kind of going back and forth in my head about what order to do things in today. I want to kind of review what we did last time. I've got a handout. We're going to work on one of the problems together, and then you guys are going to do the other problem yourself, and then we'll talk about it. And then we're going to go back and do 4.4, which is the L'Hopital's rule that I was sort of referencing before. So we're finally going to know that. There's going to be a much easier way to do some limits. Yeah! Okay. Does anyone want an example of this real quick? Like with a given function or?
Yeah, sure.
Yeah? Okay. So let's say I've got this. Right? And I want to find on the interval, let's see, 2 to 5. So I want to find all the locations C where this is true, right? So why can I apply mean values here? Why does move it work? So again,
You can take the derivative of
not
it.
just that.
It's
Continuous. On that interval, on the closed interval, and it's differentiable, meaning when you take a derivative, it's not undefined or weird anywhere in the interval, right? It's a polynomial, so that's beautiful. So when they say verify the hypotheses, blah, 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 what they mean is does it meet the requirements, those two requirements, right? So it's continuous on 2, 5, and differentiable, basically by definition, because it's a freaking polynomial. So what I really want you to know, I mean, this is so recipe-ish. Now it's built on interesting concepts, and that's how we built this, right? But now that I've got this, so what does this mean? This means that somewhere in this function, there is a location, at least one location, where the tangent line is parallel to the as the crow flies line. Because doesn't this say this slope equals that slope? And if slopes are equal, that means that two things are parallel, yes? Maybe. So how do you do this? Well, what's f prime?
It's 3x squared plus 3.
Okay, cool. And so now I know that f prime of c has to equal f of 5, bless you, right? F of 5 minus f of 2 over 5 minus 2. I'm just plugging shit in, right? I know what A is, I know what B is, I know the idea, I just throw stuff in. What is f prime of c? Well, it's just 3c squared minus 3. What's f of 5? So 125 minus 15, right?
Yeah.
So 110. And then what's f of
8 minus 6.
c?
8 minus 6.
8 minus 6, which is 2. Oh yeah. Over 3. 108 divided by 3, that goes in. That's nice. That actually goes in.
36.
36? Okay. Oh, that's nice. That's way nicer than I thought. So 3, I mean, is that cool? Is that all right? I mean, so this is just y2 minus 1 over x2 minus x1. That's all that shit is. And how do I get my y's? I plug this in. Make a slope like algebra, right? And this one is the calculus side saying, well, that's the derivative everywhere. I want to force that derivative somewhere to equal the straight derivative, the straight slope, right? The straight across. So 3c squared equals 39, right? Add 3. C squared equals 13. So c equals plus or minus square root of 13. Are both of those good? The minus square root of 13 is not in the interval. And real quick, what is the square root of 13 roughly? It's in between
12 and 16.
It's in between
It's in between 3 and 4.
Don't listen.
9 and 16. So it's in between 3 and 4. So square root of 13 is in here, yes? You guys see what I'm saying? Because if you do this work wrong and you get like square root of 28, square root of 28 is above 5, yes? So you did something wrong. It's not even in the interval. Do you see what I'm saying? So it's always good when you're doing a problem just to know, is there a quick way to get a feel for if this is at least plausible? So the negative is no good because that's negative. It's not in 2.5. Square root of 13 is in 2.5, so that at least is plausible, right? Maybe? Okay. So there's an idea this is built on, but the minute we build it up, now I've got the recipe. Right? If I really want to take that analogy, there's your ingredients, and you throw the ingredients in there. Oh, whatever, shit. Right, you get this kind of cake, the square root of 13. I like it. Okay. Now, where did I put the difference? So this is this. So, what did we do last time? There's something we knew from before. If I'm given a function, how do I find the critical numbers? Well, this is going to give it away a little bit for f prime. I find f prime. Yes? Find f prime and see where it is what? 0 or undefined. The critical numbers are the possible locations of what? These critical numbers are the possible locations of what things? I think somebody. Local maxes and mins. And possibly absolutely. Yes? So that one we've kind of been working with for a little bit. The one that's new, so this we'll find through number line, plus, minus, plus, blah, 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 blah. Increasing, decreasing, local max, local mins, right? Increasing, decreasing, blah, blah, blah. Okay. Because that's what slope tells me. Where's it going up? Where's it going down? That's crazy. So the new thing was this. So incredibly enough, I still find, the great thing is whatever the critical number for whatever derivative, I just find that derivative and then find where that's what? Where it's 0 or undefined. And these critical numbers are the possible locations of what things?
Inflection point?
Inflection points, right? So now we'll find through the good old number line, or the big ass box thing if you want to do the book's crazy ass shit. It's up to you. Through the number line sign diagram thing, you can find, what would a plus mean?
That's increasing
No.
Oh, it's concave.
Cup up, concave up. And a negative would mean concave down, blah, blah, blah. So you can find intervals where it's concave up, intervals where it's concave down, and inflection points. I like it. Concave up, concave down, inflection points. Yep, man. Okay. So what's really interesting to me is first derivative, you do this shit, second derivative, you do the same shit. Right? It just, you have to interpret it correctly geometrically. Right? First derivative is increasing, decreasing. Second derivative is curvature, concavity. Okay. And then, so we're going to do that together. We're going to do one of these problems together on this little worksheet. And the last step is going to be put all this shit together and graph this thing by hand. Okay, so let me give this to you, and we'll work on this thing. Let me give myself one. We're actually going to work on number 2 together, and then I'm going to have you do number 1. Figure I'm continuing this semester. I'm trying out what it feels like to be nice. We'll do the harder one together. you're right.
Oh, it is not. Just gotta turn it on.
All right, so look at number 2. See if you can do something there. I'll catch up here. Oops. This one. Does anyone see the domain? Anyone see what the domain would be?
0 to positive infinity.
Say again?
0 to positive
Yeah.
infinity.
Does it include 0? Yes, good. That will help us graph this thing, because now I know I can not give a shit about below 0. It's not going to show up now. Let's see, how should I rewrite this so the derivative is easier?
X to the.
X to 1/3.
X to the 3
Here.
halves power.
Yeah, the power on the top, because they're powerful. Roots on the bottom, just like on most planes, right? What's the root here? 2. So the roots are on the bottom. Power's on the top. So that's x to the 3 halves. No, I'm sorry, I didn't hear. 3x to the
1 half.
1. Now look, first power, but a second root, right? So let's see, let's do this together. What would f prime be? What about this guy?
X to 3. Well, 3 halves X to 1.
Good? No. 3 halves bigger than 1, so I subtract 1, so positive. Minus. Is that cool, everybody?
Negative half, I guess, right? No.
Well,
Oh,
1
I
half
see
comes
what-
down, there's already 3 there, so. Right, 1 half comes down, there's already a 3.
3 halves.
3 halves. X to the now come in.
Negative.
Now come in. What is this?
Negative 1.
Negative 1.
Negative 1 half. Oh. So, does that look like what I say it should be?
No.
Not yet. Well, what can obviously come out?
3 halves X, negative 1 half.
Good. So when you take powers of x out, you always take the smallest power out, right? If I were going to factor x squared minus x to the 4th, I would take a squared out. And x squared is the smaller power. So you just always take the smaller power out. Now, here's where things get interesting. I really want this to be second nature. Anytime you take something out, you're dividing it. What do I do with powers when I divide like basis? Subtract. So I'm really going to do inside, I'm going to do that 1 half power minus negative 1 half. So 1 half plus 1 half, you get a whole x, right? I really want that just to make sense. When you take shit out, you're dividing it. What do you do with powers when you divide? You subtract. So the next one's easy. I took the whole damn thing out, so what's left over there? Exactly what it say. 1, right? Okay. Now somebody really smart out there is going to go, well, I could get there, and then I could just copy what you did. But yeah, I just gave that over. Obviously, some of these are going to have more than one step, so you got. I have had people do that. There should be more than one step, but they'll do the derivative and then they just copy what I put. I'm like, how the shit did you get from here to there? You got to show them. All right. What are the critical numbers in 1?
1.
1. Zero.
Why is 1 a critical number?
So X minus 1 equal.
Yeah, it makes the derivative 0. Nothing else makes it 0, but what's the other thing we think of to find critical numbers? Where the derivative is 0 or
Undefined.
undefined. So of course, what makes it undefined?
Just making it 0 in the first place. Just making it 0.
0, yeah. 0 makes it undefined because it's x to the negative 1 half to be 1 over 0, right? So those two are critical numbers for kind of two different reasons, right? Let me stop for a minute. Just let me know if something's not making sense. Okay, now we make a sign diagram. This is the first time we're finally going to see this show up here. Oh, this is so exciting. What am I going to put over 0?
See,
No. U. Because of what we just said, right?
oh yeah.
0 makes it undefined. So just being nice to myself. I'm just reminding myself that that's a particularly because it's undefined. And that will help me later. Well, we'll see. When I draw the little sketch, at 1 is going to be flat, but at 0, what do you think it's going to do at 0?
It's not gonna exist at all.
No, the function exists at 0, doesn't it? Wasn't 0 in the domain? Okay, so what's one way for something to be undefined?
It's gonna go to infinity.
Yes, and what's weird is the function is not going to go to infinity. The slope is going to go to infinity. So it sort of like does this. And we know what a square root looks like, doesn't a square root? Let me see if I can do it from your perspective. Here's 0, doesn't a square root do this? Doesn't it get steeper and steeper until right at 0, it's infinite. So the tangent line here would be straight up and down. Maybe? That's the most direct thing that undefined means is it's infinite there. Not the function, but the slope of the function is infinite. And of course, all this part we don't give a shit about. Why? Because I already told myself I don't have to worry about that. So let's see. What if I plug in there like a, who wants to pick a number in here?
0.5.
2, 5.
I'm going to pick 1/4. So this would be positive. Well, it doesn't really matter. The square root of something has to be, by definition, positive. Yes? And this piece, of course, is going to be
Negative.
Negative.
negative. So negative, negative, negative. I picked 1/4 because you can take the square root of it easy, but I don't care. I just need to know what the sign is. And then, of course, anything above 1, what's going to happen? This piece is still positive. It has to be, this piece will be positive. There. So it sort of looks like this. Undefined, it starts off going straight down, then it gets flat, and then it goes up. I kind of missed the flat point, but anyway, a little off. Straight down, then it eventually becomes flat here, and then it goes straight up. Not straight up. So are there any local maxes? Nope. What about a local min? Yeah, 1, comma,
3. 3?
no.
No. Wait. 1.
Square root of any 1 is 1, minus 3, square root of 1 is 1, so 1 minus 3,
Negative 2.
negative 2. So on what intervals is it increasing? Well, just 1, right?
0.
No?
Oh, wait. 1 to infinity.
1 to infinity. What intervals is it decreasing?
0 to 1.
0 to
1.
1. Okay, go on. Let me stop for a minute. Are you guys? Is everything what makes? I don't care about this specific problem at all. I don't give a shit about this problem. Yeah, you heard me. What matters is, do you understand the question of what it made me do? Like why I did what I did to get the answer to the question. I mean, once I make that sign diagram, the beautiful thing about this is I can just read all the answers right off of that thing. Right? Maybe. I mean, on one level, it should be almost too nice to believe. I just got to make that stupid little sign diagram, the interval, the number line, and I answer all those questions. It's crazy. Let's see. So now let's do this. Now watch. I want you guys to notice something. I want to show that the second derivative is this. What was our first derivative?
3 times x to the negative 1/2 times x minus 1.
If I start here, what do I have to use? Like a
Product rule.
use product. Isn't that first line also the first derivative? Isn't this the first derivative also? Didn't we just like factor it? Wouldn't you rather start, I don't know, it's up to you. It doesn't matter. You could use product rule on the factored form. Well, I'm just gonna do the frickin' unfactored part. I don't know if you guys understand what I'm saying. Both of those are the first derivative. How do I find a second derivative? Take the derivative of the derivative. So either one of them you can work with. One of them requires a product rule. One of them doesn't. So I'm going to start with this. And let's see, what do we get for the second derivative? What happens here?
1/2 times 3/2.
Good?
3/4.
3/4 x to the
Negative 1/2.
negative 1/2. And then what happens here?
Positive.
Good. Positive 3/4 x to the
Negative 3/2.
negative. And just to remind you guys, I don't know if anybody uses this, but when I'm taking a derivative and I see a negative 1/2 power, I take the top, negative 1 minus the bottom 2, negative 1 minus 2 is negative 3, and then I put it back over 2. Bam. And now I can just factor this. So 3/4 obviously comes out. I'm going to take out an x to the what?
Negative 3/2.
Go to the smaller one. See if you guys are cool with this. Negative 1/2 minus negative 3/2 is negative 1/2 plus 3/2, which is 2/2, which is a whole x. And again, we took this whole damn thing out, right? So there we go. Yay! Okay, maybe. And now we basically redo what we did earlier for the first derivative. What are the critical numbers?
Negative
Get
1.
something interesting here.
Negative
So
1.
we'll get -1
And 0. Now what's weird about one of those?
It's not in the domain.
Yeah, negative 1's not even in the domain, so screw him. Yeah. Do you guys see that? That's why first step is the domain, because it kind of helps you as you go through to see what do you have to pay attention to and what can you throw out, because it's not even, so of course negative 1's out. Yeah, so let's make the sign diagram. I've only got the one critical number. This one's a little bit lame. I don't know if you guys understand there can't be an inflection point because nothing's happening on that side, right? So look, what do you expect to happen? What is this concavity of this image I drew up here? That's concave up. So I expect this to all be positive. Well, let's see, if I plug a 1 in, positive, positive, 1 plus 1, positive, there, it's all positive. It matches with what I kind of knew from before. So it's always, so it's concave up from 0 to infinity. And are there any inflection points? No. Well, if it's always concave up, there's nowhere that it changes concavity, so there's no, yep. Okay. So we did a lot of freaking work. Right? So here's the hard part. Oh, well, here's what could be difficult. I'm going to try to make this easy on you. We found a minimum, right? 1, -2 is the minimum. So let's kind of circle what's really important. I kind of know what the shape already looks like. So this one's not going to be really honest, this part was a little gross, but the graph is going to be almost too easy. Intercepts. How do I find the intercepts?
The original graph.
How do I find the intercepts of any function? How do I find the y-intercept of a function?
Find where it equals 0.
Oh, no. Let x equal 0. Right. To find, listen to this. in my last math class, I had an equation that had 11 variables in it, right? And I wanted to find the W-intercept. You with me? So I had 11-dimensional space equation, yes? Holy shit! So how did I find the W-intercept? I made all the frickin' other letters 0. So it carries throughout all of mathematics. If you want the intercept for a certain variable, you make all the other variables 0. That's it. So if I want the y-intercept, x is the only other variable. Make it 0. If I make it 0, what do I get?
0.
I get a frickin' 0. Now to find the x-intercepts, what do I do? Let y equals 0. So then you get 0 equals, let me write this like this, x to the 3/2 minus 3x to the 1/2. Can somebody help me out how to solve that? How do you solve 0 equals x squared minus 4? 0 equals x squared minus 4. What would you do to solve that?
Add 4 square root.
You could, or you could factor, right? Factoring is the more safe way to do this. So what comes out?
It's
To the 1/2.
Good, smaller. 3/2 minus 1/2 is 2/2 is 1. X and 1/2 comes out. So now I can see 1 is 0, which we kind of already knew, right? So we already knew that one. And the other one we didn't know is 3, 0. So that's also an x-intercept. Now what kind of scale can I use? Did I have any important points? The minimum is 1, -2. The intercepts are 0, 0, and 3, 0. I can make my scale just by 1, right? There's nothing. So if my intercepts were like 3,62, yes, then I probably want to make a scale that's maybe by 20s or something. Yes? So the last thing you have to really worry about is the scale. And it's going to be based on all the important points you're supposed to capture, right? So I can just use a scale of 1. I don't care about this whole side of this thing. So let's see. At 0, it's 0, yeah? We got our intercept. At, where'd it go? Yeah, at 1, it's -2. And this is a minimum. So here's my suggestion to you. You figure a scale, you plot your important points, and you label them. Because now as you start to come in with you're like, oh, it says min, so I better turn this way, right? If it said IP, that would mean, you gotta love inflection point. If it said IP and I'm coming at it like this, then my concavity has to change as I go through it, right? So if you label the points and you start to draw, you're like, oh, this is telling me to change the concavity. Okay. Okay. So now I basically got it. In fact, I already know that was the shape for my rough ass sketch. So it should start off going straight down and then comes over. Oh, I did plot my other intercept, 3, 0. And then it goes like that. Crazy. Did anybody graph this in their calculator? And again, I highly recommend you don't graph it before you try to plot it. Right? I need you to understand, if you make a mistake in your work, I want your graph to show that mistake. If your graph is perfect and your work sucks, you're going to lose more points. Because what's the important thing here? Can you translate what you did into a visual? So if you make a mistake, you're going to lose points for that mistake, but if it shows up in your graph, beautiful, you represented that correctly. I'm not going to take points off your graph then. If your graph is perfect, screw you. You just copied it straight out of your calculator, right? All right, and that's no good. That's never good. Okay. So, you guys do this here, do all the basic work, and then we'll kind of come in and do the graph together, I think, because this one is should have some inflection points. Obviously, you can use other paper if you need some more room on there.